In this example, we're being asked to find the tangent plane to a surface at a given point. We're going to use the formula for determining the tangent plane that involves the first partial derivatives. So the first thing that we need to do is evaluate the first partial with respect to x and the first partial with respect to y. So the first partial with respect to x is going to be holding the y value constant. And so our numerator is going to be 2x plus 0 because all of this is being held constant and the derivative of a constant is 0. And then we're dividing by 10 because that 1/10 is being treated as a constant multiple. So this then simplifies down to being x over 5. The first partial with respect to y is going to hold the x values constant, so we end up with 8y over 10, which simplifies down to being 4y over 5. Now we'll need to evaluate these first partial derivatives at the domain element. Well, the domain element is going to be the xy values of the ordered triple where we are tangent to the surface. So we're simply going to plug 2 and -2 into the first partial derivative function, and we end up with, when x is equal to 2, we get 2/5 as the output. This is the slope of the line that's tangent to the intersection curve at the ordered triple 2, -2, 2. And then when we plug 2, that domain element, into the first partial with respect to y, we're going to plug the -2 in for the y value, and this gives us -8 divided by 5. So here we're going to plug these values into our equation. We have z minus z naught. Z naught is going to be the z coordinate of our ordered triple. This is x naught, y naught, z naught, the point at which we are tangent to that surface. So z naught is 2 and we are z minus 2 equals the first partial evaluated at the domain element, which turned out to be the first partial with respect to x evaluated at our domain element, which was 2/5, times x minus the x coordinate of our point was 2, plus, I guess actually we should say minus because this partial is a negative quantity. The first partial with respect to y evaluated at our domain element is -8 over 5, and then we have y minus y naught. The y coordinate of the ordered triple was -2, so that's y minus -2 or y plus 2. And basically this is it. We can use algebra to change the form in a lot of different ways, but one of the more common things that you might see is to solve this for z. So we would add 2 to both sides and get z is equal to, actually we'll add that 2 here to the front, so z is equal to 2 plus these partials multiplied by these binomials. So this is the equation of the tangent plane. Let's take it into GeoGebra to check. So here we are in GeoGebra, and I've already put in the surface function x squared plus 4y squared all divided by 10, and you can see that what we have is an elliptical paraboloid here as that surface. Now let's plot the ordered triple, and so I'll need to use a capital letter here, open up the parens. Our ordered triple where we want to be tangent to this surface is 2, -2, 2. And we can see that ordered triple has popped up over here on the other side of the surface. And now we want to try to determine whether or not our tangent plane is correct. Here I'm wishing that I had maybe simplified it a little bit more algebraically. So we have z is equal to 2 plus 2/5 times x minus 2 minus 8/5 times y plus 2. And when that plane comes up, we can see that it actually is tangent to our surface function at the ordered triple. So our answer appears to be correct.